you can do your mining. Actually, these things should be, this should be G2, that should be G3, because that's shifted when I copied it. So anyway, there's 3 graphs, right? And the goal is to find frequent subgraphs with support 2. Now, one thing to note is that normally when you're doing this combinatorial enumeration, like you're discovering single edge patterns, 2 edge patterns, 3 edge patterns. So we know that we really cannot push this forever, right? Because the problem is that there are too many frequent subgraphs. And so, imagine that there is a pattern with, let's say, 60 nodes. Okay, so 60 nodes you have. Now, if you do it this way, one edge at a time, one edge at a time, there are generally, there are 2 to the 60 possible, there are exponentially, many subgraphs before you can reach that very large graph. So we know that this will never finish even in the age of the universe. No matter how much compute power we throw at it, you really cannot find very large patterns. You can find patterns of size 10, size 20. If you push it, maybe you can find bigger patterns. But we know that fundamentally, the problem is just too hard. So I'm going to talk about what to do in those situations. Right? So if you really want to discover large patterns, you cannot do it in this manner. So one option is that instead of enumerating everything, you enumerate only the largest patterns. So you can do maximal mining. Okay, so maximality is something which says that if I give you a data set, I don't really care about all the small patterns. Give me the largest. Okay, give me the maximal subgraph you can find. So this would be in terms of containment. That means every other subgraph is going to be a subset of one of the set of maximal patterns that I find. So here's an example of a maximal pattern in this small data set with the minimum support is 2. Okay, so this pattern should appear in two of those graphs. So it appears here and it appears there. And because this is maximal, it also means that all of its subgraphs are going to be frequent. So this appears 2 times. That means, of course, AAC must appear at least 2 times. AAD must appear 2 times. AC and D should appear 2 times, right? So all the subgraphs that you can create are going to appear at least 2 times. So maximality is a very good notion because it sort of says that don't worry about these small patterns. Try to find the largest one. So what we can do is we can sort of do a depth first search. As opposed to enumerating everything, we try to find only the largest subgraphs. So that actually helps and these are going to be much smaller. Right? The set of all the maximal patterns are going to be much smaller. And this is another maximal pattern which appears again 2 times. ADB, ADB over there. There's no ADB in this one. So the isomorphism of the embedding that we're counting. So there are 2 of them. And so these 2 patterns are these are the maximum. These are the maximal patterns. There are no other larger patterns you can find with support 2. So instead of enumerating everything, I can just tell you that these are the 2 largest patterns which are frequent, and that is usually, it can be used as for many applications, that should be enough. That I can find the largest pattern. And so now actually, if you do this, it's actually possible to find a size 60 graph because you don't have to go through each and every subset of that. You can directly jump, right? So in actually 60 steps, because every time I'm adding one more edge, so assuming that I have a pattern with 60 edges in it. So every time I do this, I just add one more edge. So it's actually possible to find possibly, very large patterns. But this time we only find the larger one, and we don't do all the possible things along the way. So that's one thing we can do is to do this sort of maximality-based approaches. And this is showing the same thing, when you have just one input data set, right? So this is just, when you have a single input data set, then as I said, you have to change the notion of support. And this again is a maximal pattern. But this time you have to sort of enumerate, where it appears. It actually appears 6 times. There are 6 different embeddings for this one. So there's 1, 2, 3, 4, 5, and 6. So those are the, if you look at the total count is 6. So it appears 6 times. So that would be the full embedding support. And then you can do other things like I mentioned before that. Normally we change the definition. So I'm not going to go over that part. But the point is that again you can find maximal things, whether it's a single graph or a so I'm going to skip this because we did this last time. So now the other approach. So the other approach is that you can do sampling. So I just wanted to mention this as another possibility. So one thing is you try to enumerate everything. So I say here's my minimum frequency, okay, and now find out all the subgraphs that are frequent, right? Or I might say, okay, find me all the subgraphs that are maximal and they're frequent. So they're maximal frequent subgraphs, like I just mentioned. So that will shrink down. So conceptually, what we're doing is like this. So I mean, this figure may not be exactly clear, but the idea is that you can imagine that you have a database, right, of graphs or a single large graph. This is the space of possible patterns you can have. Okay, so this space, before you start the mining, this space is unknown, because that's the goal of mining, is to discover. So each star is a frequent pattern, if you will. And so the point is that you want to, I want to twist this off. Okay, so the idea is that you start with the empty pattern, right? You do all the single edge frequent patterns, all the 2-edge patterns, all the 3-edge patterns, and so on. So normally we go either breadth first, depth first, different ways of doing this. And so you keep on finding and extending till you hit this border, right? So conceptually what happens is that there is this dark line, it's called the border between the frequent and the infrequent. So that means if I pick a pattern here and I try to extend it, it will become infrequent because there's no other extension I can add. There's no other edge I can add. And if I do add one edge, then the pattern becomes infrequent. So there's always this sort of a demarcation line, or the border between the frequent and the infrequent, or the patterns that are not frequent. And so the maximal guys are the patterns that actually sit on that border, right? Because they're the largest frequent pattern. If you add one more edge, that's what maximality means. Maximality means that if you add one more vertex or if you add one more edge, the pattern can no longer be frequent, right? That's why it's called maximal. So all the maximal guys sit on that border. So conceptually now you can see that if you try to enumerate each and everything, the space can be extremely large because normally you have this combinatorial blow up. If you look at how many graphs I can have with 2 edges, with 3 edges, with 4 edges, it keeps on going up and up. But of course the frequency then keeps it down. So you sort of expand and then you shrink because at some point your frequency threshold kicks in, you start tuning things and your pattern space shrinks. So conceptually the pattern space kind of looks like this. I mean, kind of like expansion and then shrinking. And so these maximal guys are obviously a lot fewer than the whole thing. So if you just mine the maximal pattern, then you're much better off. But sometimes even those can be extremely large. So then the question is that can you actually sample in this space? So the sampling would be, again, this notion of random walks. Okay? So we saw random walks last time in the context of centralities and things. But actually you can use random walks on this space. Now this you can also think of as a graph. But it's a different graph. It's a graph of patterns. One pattern is connected to another pattern based on adding one more edge or removing an edge. So basically, to go from the empty pattern to the pattern with one edge, you basically add an edge. Going from here to here, you add another edge, right? So each node here is actually a frequent subgraph. And so now we don't know the space. So this is the key difference, that normally we know the space of the graph you're trying to do. Here, this is what you really want to mine. So you really don't know the space, but you want to search that space. You want to basically randomly walk. It's like, think of how the ants search for food, right? They essentially go in all random directions. They leave these pheromones. Someone finds something and they come back, right? So it's pretty much a random walk, and they're extremely effective in finding food. It's kind of like the same thing here, that we're doing, you can imagine ourselves to be ants, crawling in this space. And every time you find a frequent guy, you report it. And then you say, okay, let me add a few more edges and keep on walking in this space. So you do a completely random walk, and that can actually help you, sample. So let me illustrate the idea in a little bit more concrete manner. So, let's say you start with this there's the same input data set. There are those 3 graphs. And so you just pick a random edge, okay? In this case, I chose AA as my starting point. And I'm just going to see whether this is frequent or not. So it is frequent because it appears in both those graphs, right? The minimum support is 2. So if it is frequent, then I'm going to extend it. Again, do a random extension. So unlike last time, where we did a very systematic, rightmost path, all those orderings and, loops and forward and backward edges, here we're going to do a random extension. Just pick a vertex and try to add something to it. So you might say, okay, let me, add a B to that A. Just at random. Just pick a label, put an edge. Now you see whether it is frequent in my data set or not. Turns out that this pattern doesn't exist. It only appears here. It does not appear in any other. So it's not. Basically it was a failure. My random guess did not work out. So that's not a problem. I'm just going to backtrack and try something else. So say, okay, we reject this, and I go back and I basically try some other extension. Okay, this time I got lucky. Okay, so when you did this extension at random, I find that there's an AAC here, and so that's frequent. So let's continue, right? So what my goal is to find a maximal pattern very quickly. And so just by random extension I can do this. So now I say this is good. Let's try to extend this by 1 edge. So I try something. Turned out that it's not frequent. Okay, we try something else. So I try this. Okay, again a failure. I try something else, and this time I again get lucky. So I add this B from that A. It turns out that both these, subgraphs have it. So again, we're going up and up. Every time we keep on adding a new edge. So the pattern grows. There are some failures, there are some successes. Now maybe I want to add that loop, but I find, that loop doesn't exist here, that loop doesn't exist here. So that's not a good trial. And this is how you keep on continuing. Now the question is, when do you stop? So the stopping criteria is that you try all possible extensions from this one. Okay? You try from here, you try from here, you try from here, you try from here. You try to add those loops, right? Every possible extension, and we know how to do that, right? So now we know systematically how we can explore all the extensions. Let's say you tried all of them, and none of them is frequent, then I know I've reached a maximal pattern, because there is no other extension I can add, and then I can stop. So I've found one maximal pattern. So it looks like a lot of work, and it is a lot of work, but it's still much faster than trying to enumerate everything, right? Because I'm going one edge at a time, I'm growing up and up. So this is like a depth first, random, maximal, extension. So this actually is, conceptually, is actually much faster than enumerating everything, and it works out pretty well. So this is kind of like the conceptual space. So in fact, in this database, this is all the possible patterns you can actually find that are maximal. And I showed you there were 2 maximal patterns. The guys that don't have any other, parents, they are the maximal patterns. So there's one here and one here. I don't know if you can read it in the back, but this one was one of those, patterns, and the ADB was the other pattern. So this is what the space looks like. Now, like I said, you don't want to enumerate everything, but you just want to enumerate that, and you just want to enumerate that. So the maximal patterns can be enumerated very fast. And not only that, what we want to do is we just want to sample. So essentially, when I talked about this, this is the graph I'm talking about on which you do the random walks. Now, but this graph is not completely known. So you have to try extension. So what you do is you start from the empty pattern. You just guess something like the AA I guessed as the, if I get lucky, I find this one. And then from this, I pick a random edge and I try to extend it, so I might come here. From this, I have to try many extensions. And all of them will be failures. I'm not showing all the failed attempts. I'm only showing you, if you get success, you get here. So there are different ways of reaching. So this pattern will be reached from many different paths. This pattern will not be reached from too many paths, right? You have to have, either you have to come from here or from here to get to that point. So again, it depends on how the space looks, who the maximal patterns are. But essentially, it's like you're doing a random walk in this space. So you might find one, this would be one attempt. And there are other attempts and so on. So this, I'm just going to stop here just to say that, there are other approaches. The only thing I'm going to say about this approach is that there's no guarantee that you found everything. Because I'm just doing a random, completely random walk. So sometimes, you can imagine where the space, some pattern is extremely isolated, right? It's in one part of the space, everything else is in the other part. And you keep on Right, so if I do multiple random walks here, what's likely to happen? What's likely to happen is that I find that guy first, I run this once, I find a pattern. And now I have to repeat the whole thing again. Start from the empty pattern and do another random walk. So I start from here, this time I might come here, then I might go there, and then I again end up there. So what you've done is you've found the same pattern again, right? Because multiple paths lead to it. So every different walk, there's a lot of chance of finding the same pattern over and over again. A third time I walk, I might go this way and I might end up here. So then I find a new pattern. So what you have to do is you have to see how many new patterns are found as you increase the walks. So this is an example of that. It's not a very nice graph, but it conveys the basic idea. On the x-axis, I'm showing you how many walks you have to do, okay? How many walks you do. So this is 400 walks, 800, after 400 walks, after 800 walks, after 1200 walks, how many new patterns have you found? Okay, so this is showing you the number of new patterns found. So initially, as you increase, you keep on finding new and new things. Okay, so new patterns are being found. After about 1200, I go from 1200 to 2000 walks. I have done 800 extra steps, okay, 800 extra runs of this approach. And this doesn't really increase the number of new patterns found by too much, because that means more or less you converge. I cannot guarantee that, but empirically you sort of converge to, you're not discovering new and new things, right? So every time so this is just showing you that this is typically what the curve would look like. That initially you'll find lots of new patterns, but at some point you stop finding patterns. So there is, at the end of this process, let's say I've done 2000 walks. Now I have 2000 patterns that are possibly maximum, but many of them are duplicates because I've reached the same pattern. Right, so in fact, in this data set there are only 90. I know this because I actually knew the right answer. There are 90 maximal patterns. Okay, so but I did this 2000 runs to discover those 90 patterns. In this case, I actually found all of them, but the point is that you have to eliminate duplicates. So out of those 2000, the vast majority of them are going to be repeatedly finding the same pattern over and over again. So again, that might look like a waste, but this problem cannot be solved if you do this complete enumeration, because this has a pattern. I'm not sure. Let's see if I can remember what the largest pattern size was. But to give you an idea, like the G-span algorithm, right? I ran that G-span algorithm for 1 day, okay? And for the entire day, I let it run, and it had basically output. So this is a small data set actually. This was a data set of 3, biological graphs. So there was a gene expression graph, there was a protein interaction graph, and there was a metabolic pathway. And I just wanted to see, are there common elements across these 3? So the input graph has only 3 megabyte size, okay? But when you run G-span, it's trying to find all the single edge, 2 edge, 3 edge, 4 edge, 5 edge. So it keeps on doing that, and after 1 day I saw it had output 8 million subgraphs and 7 gigabytes of output. Okay, so this is like a reverse data mining. You're not really discovering any insights. I mean, you're taking a small data set and you're blowing up the pattern space. So this is like what really happens in practice, that you have to make sure that data mining can actually help you understand things and not make it worse. So as I said, I stopped this after 1 day, but this sampling process, actually it just took under 5 minutes. So I did these 2000 walks, I found 90 maximal patterns. And so you can see the power of running the complete thing versus just sampling quickly. Now the problem here, as I said, is there's no statistical guarantee. So I can do this random walks. So there are approaches to actually fix that. So there are these Markov chain Monte Carlo sampling methods, which I'm not going to get into now. I might come back to them later. But there is again a principled way of sampling. So the sampling, you can actually guarantee that you actually sample the space in some uniform way. So I can actually give you a statistical guarantee. Here I cannot give you the guarantee, but this is extremely fast. So in practice, this might be actually better. But if you wanted a statistical guarantee that you actually sampled properly, then you have to do it the proper way, which is the Markov chain Monte Carlo. So I'm not going to talk more about that, but this is a pretty much interesting research to improve the efficiency, the scalability. These are all open questions in this case. All right, so before I move on to the next sort of major topic, which is clustering, are there any questions on the graph mining part?
So I have one question.
Yeah.
So what is the basic difference between page rank and prestige?
Oh, that one. So, if you remember, prestige is simply doing the unnormalized. So you just take the adjacency matrix and you compute the eigenvector of that one and the value you get out of that. So the problem with prestige is that every node is contributing its prestige to everyone else it is connected to. So it's more of a conceptual difference. So what the page rank says is that actually you don't have infinite resources. I cannot give you the same value to everyone, because if I'm connected to 1,000 people, should my prestige be given to all 1,000 of them, right? It's like I have, it's like my prestige was 1,000, right? So what PageRank says is no, divide that value by 1,000, and then give each one of them 1/1,000 of your prestige, right? So that's one conceptual difference. So it's sort of more suited for the web and those kinds of where you have this power law type of behaviors. In a small network, it doesn't really matter whether you do prestige or PageRank, but when you have these hub nodes and things, there will be a remarkable difference in the output. So because now you have a finite resource, you can only divide it equally. So that's one key difference.
You don't need to normalize in case of prestige.
Yeah, you don't normalize. You don't normalize.
But I calculated yesterday on graph prestige, but I'm just getting increasing. It was not converting to a dominant eigenvector.
Ah, okay. Yeah, because I skipped one step.
Yep.
What you have to do is actually, and this I should have mentioned last time, when you do any kind of page rank computation, right, and you keep on repeatedly multiplying, the values will keep on increasing. So what you do is you have to normalize after every step. So normally what you should do is, after you do the multiplication, you take that vector and you make it a unit vector. Okay, divide by, or you can just divide by the maximum value. But ultimately you're going to make it a unit vector. So take the magnitude of that vector and divide by that. And so that way you keep it controlled. So that will converge to the dominant.
Sir, in its algorithm there are hubs and authorities. So suppose I have a graph. Initially, how I will decide that this particular node is hub and this particular node is authority?
You don't decide that. So that comes out of the algorithm, right? So you're computing two scores.
Yes.
So initially the scores will be 1 for everyone. So you have an authority score of 1, a hub score of 1, or 1 over the size of the network, and then you run that hits algorithm. Now what the hits algorithm will do is it will actually ultimately give a score to every node. You'll get a hub score and an authority score. So now you can pick up actually. Now you can just say, you can pick a threshold. You can say any node with an authority score above a certain value is an authority. Any node with a hub score above a threshold is a hub score. Is a hub node. And then you can see if there is a bipartite-like structure. But the point is just to find these scores. Which score is a better authority? Which web page is a better hub? So you can just do a quick analysis and find out, which of those nodes are. So you don't need to know them before.
So one question. So what property of normalization makes a matrix to converge? What property? What's the main thing about normalization? Because I'm not able to understand. Why do you have to normalize it?
Oh, no. So yes. So for the PageRank type of algorithms, I can take any matrix, right, and I can compute the dominant eigenvector. That it will still converge. Okay. The only condition really on convergence is what is known as a spectral gap. Okay? The spectral gap is essentially the magnitude of the largest eigenvector, right? And so if this is dominant, right? So that's why it's called the dominant eigenvector. So if your eigenvalue is larger than everyone else, you are going to converge. It's only when the eigenvalues are kind of close to each other, that's where conversion gets to be a problem. But this happens very, very rarely. So you can always create a pathological case and say, okay, on this graph, you're going to have a problem. But for vast majority of the cases, convergence happens rather quickly. And now, so that's about convergence. So it's nothing to do with normalization. Whether or not you normalize is not the point. It's basically the spectral gap. What is the magnitude of the largest eigenvalue? Now, for the page rank, what you're doing is you are normalizing it, and by normalizing it, you're making it into a Markov matrix. So the prestige doesn't have that assumption. So this is a Markovian assumption that you have a probability of transitioning from one node to another node to another node, and then you just do this one-step walk, two-step walk, three-step step walk. But if you are thinking in terms of random walks, then you have to normalize it, otherwise it doesn't make sense. That means every resulting vector will always be a probability vector. So that's the point about normalization, that it becomes a transition matrix of what is called as a Markov chain. That is, this chain where you just need to know the previous state, you're in a current state and you can jump to another state, and that's all we need to know. Does that make sense?
So partly.
Any other? Okay.
Sir, actually, we were running this program of PageRank algorithm and this prestige. So what we found that if the matrix is not normalized at all, it won't converge. So the basic difference, what we found that the basic difference is between PageRank and this prestige is a normalization.
No, I think that might be the question that he asked, which is that if you actually, after you, in the prestige score, right, you have a matrix, you do the multiplication, okay? So the adjacency matrix times the prestige vector, A times P. After you do that, you get a new vector, right? Now this vector, scale it, okay? Divide by the magnitude of the vector. Once you make it a unit vector, it will converge. Yeah.
In the random walk mathematical subgraph, what I did was the first time you have a random walk. Random walk.
Yeah, randomly pick an edge.
Now, in each of the graphs, I do a depth first and a depth first to find out that edge.
Sure, yeah.
That's what I do.
Yeah.
Now, but that edge may be present somewhere else in the graph also. So do just one search. I found out the first edge probably.
Okay, fine.
First edge.
Yeah, okay.
Next time I increase that pattern, I expand that pattern. Now again I do a depth first search. Every time I have from the same edge.
No, what you should do is, we didn't really talk about the matching part. But technically what you should do is you should probably maintain a list of embeddings. So the first time I pick a random edge, such as the AA edge, what I should do is I should go back to my to my database, and I should probably enumerate all the embeddings, and I just store it. So because you've got to you have to do the work anyway again later on, so I might as well do it to begin with.
So that would require only a depth first or depth first only one step in that case.
It's a little bit more involved than that, because what you have to do is, so you pick this, so like you said, so basically start with the AA, and okay, we have, basically 4 embeddings in this case. AA, because it's AA, it can be one way or the other way. So we keep all 4, and we store it somewhere. Now when I extend it, I can go back to those embeddings and see, okay, is there an extension from those? So you have to look at the neighborhood of the embedding you already have, and see whether there's a B in that neighborhood. And so this way I don't have to redo the whole computation each and every time. I can just say, go back to the previous step, look at all the embeddings, and see which of those can be extended. So in this case, one of them, like the one from this A will be able to be extended, but the one from that A, there is no B there. So now you'll find only one embedding, and that will be the one. And here you try to do the same thing. You say, okay, if this is the first A and this is the second A, and I'm looking for, this is the first A, second A, B. Is there a B here? No. And if this is the first and that's the second, then that's A, A, B. There's no B there. So there are no extensions. So the idea is you go back to the list of embeddings, and this way we can avoid doing the computation over and over again. But you do have to maintain the state. Now, and that's actually a very good point, because when you find the embeddings of an edge in a graph, or embedding of a pattern, there can be many of them, right? So there is a penalty to be paid. That is, you have to have a huge amount of storage. So there are methods like GSpan, actually, it does not store the embeddings. It does exactly what you said, actually. Every time, it will go back to each graph and try to find a match.
So the would be very frequent for us, and having to maintain all.
Yeah, all of them might be a space complexity problem, right? So if you cannot store, then you forget. You just say, I'm just going to go back. Each time I'm going to redo the whole thing over and over again. So this is a classic computation versus memory, storage trade-off. It's a very good point, actually. Any other questions? All right then. So now we move on to the sort of the next topic. So after doing the structure, the pattern mining, now we come to clustering. So I should warn you now that this clustering part will be, again, going back to matrices, because a lot of this work is actually based on analyzing certain matrices that are associated with graphs. So what I'm going to do first is I'm going to sort of recap the the matrix terminology that we need. So it was good that we did PageRank yesterday, because this is going to be, or rather eigenvector, eigenvalues, because you'll see that the same concepts are going to come up again in the concept, or in when you want to cluster things. So what is the clustering problem? So the clustering problem in a graph is, and we thought of, for the time being, I'm going to ignore the labels again. So this is purely a structural clustering algorithm. If you want to throw in labels, then you have to add other tricks to the whole set of tools that we have. So the idea is that you're given a graph, so there's a graph like this, maybe connected to something. Maybe we'll connect it some other way. So, you're given some graph. And right now, as I said, we will not worry about the labels of the nodes. Only the structure is what we're going to look at. So I say, look at this graph and find me some clusters. Okay, so find out the groupings. I mean, the way I've drawn this is pretty obvious, but if I just give you the graph, it may not be clear what the clusters should be. Right? Now, clustering is one of those things where you're trying to find groups, right? And to define groups, you have to define the group affinity, like what makes a group a group. So in other words, we need some notion of similarity. Or in the reverse, it could be some notion of a distance between points, or in this case, distance between the nodes of the graph. Because what we want is that in a cluster, right? I mean, so this is like a conceptual, like what we imagine when we say you want to find clusters or groupings or segmentation and so on. What you imagine is that people within the group have close affinity, right? Either ideals or whatever other properties that they have, they should have some very high similarity. That's what makes a group. And then you have a different group because the similarity between this group and that group should be weaker. Right? So the members within the group should be more similar. Across groups, the similarity should be less, and so on. So that's essentially conceptually what we want to do. Now I can say the same thing in terms of distances. I can say, right, so similarity is how similar I am. Distance is the opposite of similarity, how far I am. Right? So what you want is that within the cluster, the distances should be small, and then across the clusters, across the group, the distances should be large. So this notion of distance and similarity is pretty much interchangeable. Just one is larger, the other has to be smaller to make the groups. But now the problem is, what do we mean by similar? Right? What do we mean by distance? How do we actually define that? And that essentially is the key. I mean, the key first step. That till we define that, we cannot really do any clustering per se, because we're going to apply some methods. So what we have to imagine is that in this graph, I can take the graph and I can assume that every edge has, if I just consider the basic adjacency matrix, it's a binary matrix, right? So either two things are connected or they're not connected. Or I can imagine a weighted scenario where actually I put the similarity between them. I can say these two things are similar and that's the weight. And the weight can be the similarity, or in the reverse, the weight can be the distance. But I'm going to use the view right now, the view of similarity. Okay? I'm going to say that we are going to connect two vertices, and I'm going to put a weight here, and the weight will denote the similarity between the nodes. So technically there is also a similarity between these two, but the reason we don't have that edge is because that similarity is probably 0. Right? So we don't keep the 0 similarity edges. But technically speaking, one can imagine that the graph can be completely connected. It can be, every node is really connected to everyone else. It's just that some weights are extremely small, so we don't really count them. Some similarities are very small. So only the ones that have higher similarity we keep. Okay, so let's say we have that scenario. So you have a similarity matrix or the adjacency matrix, which I'm going to go over shortly. And now the goal is to find these clusters. Okay, so normally it would be enough to just give you the pairwise information, but in a graph, to find the clusters, you have to do a little bit more work than that, right? So you might want to say, so this sort of goes back to the notion of similarity. How are you going to define similarity? So the similarity can be also in terms of sort of the opposite of the distance, like how many hops it takes you to get from one point to the other. So that's a very natural notion of distance in a graph, right? And so the similarity would be the opposite of that. So the higher the distance, the less the similarity. So I can just make it, for example, 1 over the distance, I can do it that way. So that would be the similarity, 1 over the distance between two vertices. And the distance can be the number of hops. So that's the shortest path between two vertices, that's the distance between them. And 1 over the distance is the similarity. So we can do those kind of things. At the end of the day, in a graph, when you say clustering, you're basically talking about partitioning that network. Because clustering, we'll talk about the overlapping part later, but right now I want to find non-overlapping clusters. Meaning a node can only belong to one group and not multiple groups. So the question is how to partition it, right? So in this network, I'm going to say, for example, if k equal to 2, so k is this value. So the other thing you have to give in clustering is how many clusters do you want to find? So this k parameter is kind of like a very central parameter for many of the clustering algorithms. You have to tell me how many clusters to find, because I don't have any magical sort of oracle I can consult that tells me the right number. So there are some methods that will try to predict, what the right number should be. You use some, information theoretic criteria one can use. There's an entire field of statistics called model selection that essentially deals with, what is the right model, whether it should be 2 clusters, 3 clusters, 10 clusters, and other types of, similar types of questions. But let's keep thinking, you're going to tell me how many clusters to find, and I'm going to report to you how many clusters there are. So then the question is, in a graph, it all boils down to partitioning. Basically what I'm asking you to do is, how are you going to partition this network into 2 parts? So you might say, I'm going to do it this way. That means you're cutting this edge. Okay, so this edge and this edge is being cut. Right? So a clustering essentially corresponds to a partitioning of a graph. And any partitioning has what is known as an edge cut. That is, which edges are getting thrown out. And when I remove those 2 edges, I get 2 disconnected components. So each connected component is going to be a cluster. So it could have been this way, or I could have done it the other way. That would have been the second possibility, would be to cut it this way. And basically it's a question of what is the fate of this node, right? Does it belong to this cluster, does it belong to that cluster? Maybe you say actually it probably should belong to both of them, right? But then that would be an overlapping clustering. So if you're doing straight out partitioning, this node has to be put into one or the other. And that would probably depend on the strength of the connections, right? So is it more strongly connected to that, or is this more strongly connected to that? That would decide which way that node might go. So basically clustering and basically partitioning are more or less equivalent when you talk about graphs. That is, you have to partition the network, you have to cut some edges. Now, what is the goal of partitioning? Again, you want to minimize, so this is the classic sort of graph partitioning approach, where you just say minimize the edge cut. Okay, so this is a very classic notion of minimum cuts and things. So the idea is that you could think of graph mining in that sense, that okay, sort of graph clustering in that sense, that I'm going to do a edge cut and try to minimize the weights on those edges. and that will give me the partitioning into the two parts. But there's a little bit more going on than that, because you also have to respect the size, right? So because if you say I want to have two clusters, maybe the simplest thing for you to do is to actually just do this, right? So you just cut these two edges, and all of those can belong to one, So if you do a thing like a minimum cut type of an idea, it generally does not work, because it will always try to pick, one very small, portion that the rest of the graph will be on the other side. So it's not just that you have to do it into two parts or three parts, depending on what K is. K can be 10-way partitioning. You also have to have a balance condition that whenever you're doing cutting, make sure that the two sides are kind of like on the same scale in terms of the size of the clusters. They don't have to be exactly the same, but they should be respectable, clusters. There should not be like one isolated node on one side. So there's also this, so this is sort of like partitioning plus balancing. So that's the kind of the basic sort of thing, basic way in which we can understand this clustering. And then, because it's a graph, it's not just the edges that matter. As I said, it's the entire flow of information that might matter. So we also want to look at the neighborhoods and the connectivities and the clustering, right? So in a graph, you can do things 1 hop away, 2 hop away, 3 hop away, and we want to use all that information also. So in a minimum cut-like scenario, you pretty much just choose you just want to minimize the weight of the cut. But as I said, you want to do balancing. You also want to do other ideas like you can use ideas like betweenness and other things. So we'll see examples of those. That there are lots and lots of ways of actually clustering, as long as we keep the basic idea intact that we want to have this sort of tightly connected and also highly weighted. In terms of similarity, the weights should be extremely. They should be highly similar. So the weights here should be high. The weights here should be high. And whatever you're cutting, the weights should be low, right? The similarity should be low. That's where you cut. So maybe that's the clustering you get. So this is what I'm going to be talking about, how to do this. So now, so this is the basic task, that you want to find clusters. And we're going to start with sort of like this. So I'm going to sort of flip between the matrix view and the graph view. Okay? And I'm going to be talking about cuts, and I'm going to be talking about matrices. And we'll see that there's actually a very tight connection between the matrix and the cut, okay, which will become clear. So what I'm going to do first is actually take a step back, not worry about clustering for the time being, just talk about what are some of the other important matrices that we can use to represent graphs. So we already saw one matrix. In fact, we've seen two matrices yesterday. One was the adjacency matrix, the other was the degree matrix. So those are definitely going to be playing a role, but we'll have more. So the first thing to do is that we're going to start out with some assumptions. So we'll assume that you have a data set. This could be a bunch of points, whatever, and or you're just given a graph directly, okay, with similarity. But I'm assuming that you're going to, whatever your input starting point is, you have the similarity between every pair of vertices. It's n by n. So this is your adjacency matrix. It's the weighted adjacency matrix, and we'll assume that it is a symmetric matrix. So the similarity has to be symmetric. If I'm similar to you, you are similar to me by the same amount. And we'll assume that these values are non-negative. So you can have zero similarity, but you cannot have negative similarity. So these are the only two conditions we're going to impose on this adjacency matrix: the weighted adjacency matrix, or the similarity matrix. That it should be symmetric, and it should be non-negative. Each entry should be non-negative. Okay, so this is a standard adjacency matrix that we talked about. And if you have weight, it becomes the weighted adjacency matrix. All right, so this matrix is going to play a key role. Now, what about other matrices? So yesterday we talked about the degree matrix, right? So remember, the degree of a vertex is simply the sum of all the other, connections over all j. So for I just sum over all the j and look at the similarity to everyone else. So that's the degree. So this degree is the weighted degree. It depends on how similar I am to everyone else. So it's not just the number of neighbors I have, but how similar I am to those neighbors. And so I add them up into the degree of that vertex. And then the degree matrix is this diagonal matrix where it's pretty much the degree of vertex 1, degree of vertex 2, degree of vertex n. Everything else is a 0. And if I were to expand that, this would be just the sum of all the, for vertex 1. So A1j for all j. This is A2j for all j, you sum them up, and so on. So it's all the, the standard stuff. So this matrix again is going to be important, as we'll see. So we saw this last time, when we were trying to do the normalization, and this is where the normalization showed up. So the transition matrix now, right? The Markov matrix, the probability stochastic matrix, these are all interchangeable terms. When I say, the one-step transition matrix, the Markov matrix, or the normalized adjacency matrix, they're all pretty much referring to the same concept. Now, forget this for a minute, right? Essentially, it is every, the first row is divided by the degree of vertex 1, the second row by the degree of vertex 2, and the last row by the degree of vertex n. So this operation, like I said last time, can be written very compactly in matrix notation as the inverse of the degree matrix times the adjacency matrix. Because the operation on the left basically does row operations. So if you multiply anything on a vector on the left, it will divide, it will basically manipulate the rows. And of course, it is the inverse of the degree, so that has the effect of dividing by the degree. So it's 1 over, so the inverse, I should mention it here, is that the inverse of the degree matrix is actually defined as 1 over d1, 0, 0, and so on, 1 over d2, and so on and so forth, 1 over dn. So it's basically every vertex, right, 1 over the degree. So that's going to be a diagonal matrix just like this one, except that it's 1 over all those entries. So because it's a diagonal matrix, computing the inverse is straightforward. If you are not a diagonal matrix, computing the inverse is not so easy. So you have to do much more work to get the inverse of the matrix. So this is how we can compute the inverse of that matrix, and that inverse is multiplied by A to get this normalized matrix. Okay, so we did this yesterday for the page rank. So this is exactly the same transition matrix. Now, what do we know about this matrix? So just to make it clear, adjacency matrix was symmetric because we started out with that assumption. It was non-negative. This matrix is no longer symmetric because, right, I've taken the first row and divided by d1, second row by d2. So already you can see that this entry and this entry are not the same. In one case it's divided by d1, in another case it's divided by d2. Because we're just doing row manipulation. So this matrix is not a symmetric matrix, which is important to keep in mind. But we do know something about this. We know that every row will sum up to 1. Right? Just look at all the, if I add this up, this is A11, A12, A1n. That's actually the degree of the first vertex. So that's exactly what we want. This now becomes the probability of jumping from 1 to 1, the probability of jumping from 1 to 2, and so on. So this is why it's the transition matrix. Okay? So this is now a fraction. What is the probability that you remain? So the diagonal entries tell us the probability that you remain in the same vertex, and every other transition tells you how can I go from 1 to 2, 1 to n. This is the other way around. How can I go from 2 to 1? So that probability is now different. Jumping from 2 to 1 is different from jumping from 1 to 2. So it's no longer a symmetric matrix.
Sir, isolated node cases?
Isolated nodes, that's always an issue. One option is that you just throw them away because they have no role to play in the clustering. Like if you're just doing a structural clustering, if they're isolated, then they're of no value. So they're noise. The way PageRank, in PageRank what they do is they assume this random, structure that you can actually jump from any node to any other node. So you assume a complete, that node is really connected to everyone else. But with a very small, so it can jump to anyone with equal probability. like it has an extremely high degree. But yeah, I mean those are practical. When you want to implement these things, yeah, those things come and you have to account for that. So the other thing is that if you look at this Markov matrix, and this is something that you can just study conceptually what happens, we'll be interested in looking at the eigenvectors, like the page rank is an eigen, the dominant eigenvector matrix, right, for the transpose. So because each row of M sums up to 1, one can show that actually the largest eigenvalue for this matrix is going to be 1. This is the maximum value you can have. Every other eigenvalue is going to be less than 1. So this is one thing that is a basic property of a transition matrix. And one can prove this, okay? So one can show that, now because this matrix is not symmetric, you can have eigenvalues which are negative, okay? So that can happen. So eigenvalues can be negative, but the absolute value, it cannot exceed 1. So 1 is still the absolute value, meaning it can be negative 1 or positive 1, but in terms of absolute value, the largest absolute value is still going to be 1. So this is just a mathematical property, one can prove it. And there are some other things, but we'll come back to this because we're going to be talking about how to use this matrix for clustering. So normalized adjacency matrix plays a very important role. What about some other matrices? Now we come to really something we haven't seen before. So this is just an example of the adjacency matrix for that graph, the degree matrix for that graph. And you can see the degrees are laid out in that manner. Vertex 4 has degree 4. Right? So vertex 4 has degree 4. And then you can compute the the Markov matrix looks like this. And then I'm showing you what the eigenvalues are. Okay, so lambda 1 is the largest eigenvalue, is 1. Lambda 2 is, so remember we sort the eigenvalues always from larger to smaller. And so this is lambda 2, lambda 3, lambda 4 is negative, lambda 5, lambda 6, lambda 7. So the sort of the smallest in terms of the value is -7, but in terms of magnitude, the smallest is 0.045 in terms of the absolute value. So this is, I'm not showing the eigenvectors here. We'll get, but just to understand that we'll be talking about these eigenvectors and eigenvalues. And these are all of them. So it's not just the dominant one. We're looking at all the eigenvalues, all the eigenvectors. Okay, now we come to a very, very, very important matrix. It's called the Laplacian. This is sort of like a fundamental, matrix because it's a very nice matrix. Okay, it's a very nice matrix in the following sense. First of all, let me define it and then I'll talk about the properties of this matrix. So this matrix is defined to be the degree matrix times minus the adjacency matrix. Okay, so delta minus A, or delta minus A, degree matrix minus the adjacency matrix. So that's your degree matrix, that's your adjacency matrix. You subtract them out and what do you get? So you get the diagonal entries. They have everything in the degree except for what you subtracted out. You subtracted out the self probability. Okay, so this is the sum of the probability of jumping from one to everyone else other than yourself. Okay, that's this one. All right, and everything else is a negative entry, right? Because there's a 0 here, so there's a diagonal matrix. So you get minus that, and so on. Now, this matrix is a symmetric matrix. Why? Because A is symmetric, delta is symmetric, because the diagonal matrices are symmetric by definition. So when you subtract the symmetric matrices, you actually get a symmetric matrix. You don't change the nature of the matrix. So that's one good thing. So one property we have is that it is a symmetric matrix. And of course, many matrices are similar, so that's not the really interesting property. But this has a really, really important property, and this property is the positive semi-definite nature of the matrix. So let me explain what that means, positive semi-definite, because that's a key idea. So let me define what that means mathematically, then we worry about the consequences of that. So pick any matrix. Okay, so I'm going to say X is n by n matrix. And let's say U is n by 1 vector. So the definition of positive semi-definiteness is that if you do a quadratic sum, okay, if you do a product where you take the vector u transpose xu, this is always going to be greater than or equal to 0. This is the mathematical definition of what it means to be positive semi-definite. Is any. So what are we doing here, right? So let me explain this part here. So this is what I call the quadratic, the quadratic sum. And I'm going to show an example to show what's really happening. It's basically saying that if you multiply this matrix on the right by u and on the left by the transpose, you're going to get first of all a scalar number, right? So because u transpose is going to be 1 over, it's going to be a 1 by n matrix. This is of course an n by n matrix, and this is n by 1. Exactly. So you get 1 by 1, which is actually a scalar. So what we're saying is that any product like this, it's a quadratic equation in the u's, because the u appears twice, okay, on the left and on the right. So when you multiply that, it becomes a quadratic product of those two. And so essentially the X matrix acts like a weight for those quadratic sums. Okay, so X matrix acts like a weight. So these are sort of like the scalar values in a quadratic equation. And when you add them up, we're just saying that this quadratic equation has this nice property. Okay, let me just show you a small example, then we'll see. So for example, let's just pick a matrix. I'm just going to call it x11, x12, x21, x22. So this is a small matrix, just a 2 by 2 matrix. And u, so u is this vector u1 and u2. So we add u1, u2 here, and the transpose of that on the left hand side would be u1, u2. Okay, so this is your u transpose, this is your u, this is x. So when you do this matrix multiplication, right, what is the result? So as I told you before, let's talk about the right part first. So when you multiply a matrix on the right by a vector, you're doing column operations. Okay? So it's like you're taking this matrix and you're basically combining them, u1 times column 1 and column 2 times u2.
Row.
No, so I'm talking about forget about this one. Just this is a column operation. Okay, let's do it and see. Right? So if I multiply these two, so you have u transpose on the one side. What is the net result of this? So it's this times this, right?
Yes.
So it's basically so it's actually x. So okay, let me write it one way first. So it's actually u transpose, and I'm going to say it is this column. This column times u1. Okay. That will be the result. Because that's what a multiplication on the right is always a column, like the first. So in other words, the first value multiplies the first column, the second value multiplies the second column. Which you can do the full blown normal matrix multiplication, you'll get the same answer back. So what this looks like is obviously so this is u transpose x11 u1 plus x12 u2, right? x21 u1 plus 2, 2, Is that correct?
Okay, sir.
Right. So essentially, I just did it this way just to sort of emphasize the fact that operation on the right are column multiplications. I mean, you're combining. It's basically, think of it this way: it's a linear combination, okay, of the columns by these weights. So that's exactly what I did. I did a linear combination of the columns using those as weights. The U1 and the U2 are the weights. So which you could have just done it normally. You could just said multiply this by this. X11 times U1, X12 times U2, that's the first entry. X21 times U1, X22 times U2, that's the second entry. So the net effect is the same, but this is just a different way of sort of showing it. Okay, so that's that. Anyway, so when you multiply this out, what do you get? So now let's put this vector back here. There is U1, U2 here, right? So when I multiply this whole thing out, finally I'll get a quadratic sum. So it will be, now this is, this is just, the U1 will multiply the first row, U2 will multiply the second row. So you're going to get U1, X11, U1, plus U1, X12, U2, plus U2, X21, U1, plus U2, X22, U2. So this is what I was saying. It's a quadratic equation in the U's. Okay, so the x's are just they're acting like the scalar value. So you're taking the entries of x, and it's a quadratic sum. So it's u1 squared times x11, u1 times u2 times x12, and like that. So it's a quadratic equation in the u variables. So anyway, this quadratic sum being greater than or equal to 0, it has to do with the curvature. So if you were to plot this quadratic equation, it becomes a parabola. Okay? And positive summation definition basically says that the parameter is basically greater than or equal to 0. It always remains above the 0 value. Okay? So all that is fine, but what does it have to do with the property that we want to study? The consequence of this property, the fact that it's positive semi-definite, it has very, very nice properties, which is your eigenvalues are all also non-negative. So you cannot have any negative eigenvalue. And the fact that it is a symmetric matrix will mean that you have only real values. So every value, because normally when you take a matrix and you do the eigenvalues, you can have complex values that can come up. Okay, so numbers don't have to be real. Even if your input matrix is real, the eigenvalues can be complex numbers. And complex numbers are hard to interpret. But in this case, we can show that all the lambdas, so the consequence of this is that, i's are greater than or equal to 0. And they are going to be, of course, also real numbers. So that was sort of an aside on this notion of positive semi-definite. So what you can do now is that this Laplacian matrix, it is going to have non-negative. That means I know now for a fact that lambda 1 is greater than lambda 2 is greater than lambda n, and the smallest value can be 0, but it cannot be lower than that. Okay, and we also, one more thing, the rank. So if you look at each row and you add them up, each row adds up to a 0. Okay, that's another way of saying that the rows and the columns are linearly dependent. So if you take a bunch of vectors and you add them up and you get the 0 vector, that means there is at least one vector that you can throw away from that. It's not completely a set of linearly independent vectors. So that means the rank. So you remember I had mentioned this last time that the rank of n by n matrix can be at most n, but if let's say 2 rows are the same, then the rank has to be at least 1 less than n. In this case, we can guarantee that at least one of them, because the smallest value is going to be 0, because everything adds up to 0. That means if you look at that equation, L times lambda equal to L times u equal to lambda u. So at least one of the values has to be a 0. One can show that. So we can say the rank is at most n minus 1. Anyway, so this is, again, I'll come back to this when the main point here is that the eigenvalues are all non-negative and they're real. Okay, so that's that. So here's an example. for the previous thing, this is what the Laplacian matrix looks like. And if you compute the eigenvalues, you get this set of numbers. So the largest one is 5.6, 4.6, and so on. And the last one, because it's a 7 by 7 matrix, the last one will always be 0. There can be more zeros, but there is at least one 0. Okay? How are you doing with that? Can you take a break? Okay, so we'll continue from here because the next part of the lecture will be on how to use these matrices for clustering. Because right now we just talked about the matrices as a general thing, but we haven't really talked about why do they show up in clusters. So how long a break? 5 minutes break and then we'll reconvene.